In front of us is a related rates problem from a Calculus 1 course. So the following says that coffee is draining from some conical filter into the cylindrical coffee pot at a rate of 10 inches cubed per minute. Reading through that, I noticed that I'm going to need some information, or that information is given to me. Whenever I hear rate or rate of change, that's telling me that it's telling me a derivative. And so in this case, it's telling me that the rate that the coffee is flowing out is 10 inches cubed per minute. And so that's telling me that my volume is changing. So I know that the volume changes at a rate, dV dt, V being the volume, dV dt being the derivative at 10 inches cubed per minute. Part A wants us to figure out how fast is the level in the pot rising when the coffee in the cone is 5 inches deep. Okay, so first of all, how fast is that level in the pot rising? So looking at that, it's a cylindrical coffee pot. And so I need to look at what is the volume of my coffee pot. So the volume of this coffee pot, well, volume of a cylindrical is pi r squared h. So r being my radius, I'm given in here that the diameter of the bottom of the base, which is the same in that pot, is 6 inches. And so if my diameter is 6 inches, I know my radius is half of that. So my radius is 3 inches. So let's go in here because our radius is not changing for this bottom piece of the coffee pot. And so let's plug in 3 inches for R. So we can rewrite this. Our volume of that coffee pot is pi times R, which is 3 squared times H. So our volume is 9 pi H. We're looking at trying to find the rate of change in the rise in the coffee pot. So rate of change, that rise is talking about the height. And so I want my volume in terms of H. So that's great. It already is. And since I'm wanting to find the rate of change of that height of that coffee pot, that tells me that I need to find the derivative there. So let's look at the derivative of both sides of our equation. So looking at, because it's an equation, I can look at the derivative with a rate of time for both function. So remember, our volume is changing with a rate of time. So if it helps you put it VT is equal to 9 pi, and our height is changing with a rate of time. So it's a function of t, h of t. And if I take the derivative of one side, I have to take it of the other side. Okay, so the derivative of my volume is dV dt or V prime, depending on how you want to write that. Since I wrote it as dV dt above, I'm going to write it here. So dV dt is equal to, so taking the derivative of h of t, that's h prime of t, or h of dH dt. So this is equal to 9 pi dH dt. Well, we know what the rate of change is of the volume. We were given that was 10 inches cubed per minute. So we have here that 10 is equal to 9 pi times dH dt. If we divide both sides by 9 pi, we get our rate of change of our cylindrical coffee pot. The height is changing at 9 pi, 10 divided by 9 pi inches per minute. Okay, so that was for part A. So for part B, how fast is the level in the cone falling then? Okay, so since we're looking at the level in the cone, we need to look at the volume of our cone. So if we're looking at the volume of the cone, a volume of a cylindrical cone or conical filter, whatever that is, it is our filter. That is V is equal to 1/3 pi r squared h. The problem in here is I don't know what the radius is as that is falling. If it was to the top of my cone, I know that radius in here is 3. So we want to create, and we know what the height is when the radius is 3. When the radius is 3, that height of that cone is 6. So let's make another triangle because we're looking at when that height is 5. We don't know what our radius is. So let's just, right now for that height 5, let's just put that h. So we have similar triangles here. I know that 3/6 is equal to r over h. I want to rewrite my radius in terms of height. I want this function over here for the volume of that cone to be just in terms of, in this case, I'm looking at the rate of change of the height. So I want to keep that in terms of height and not height and radius. And so I'm going to look at this similar, this proportion that I wrote out, and I'm going to find r. So I'm going to rewrite this. This is 1/2 is equal to r divided by h. If I multiply both sides by h, I get r is equal to h divided by 2. So I'm going to go back in here and I'm going to rewrite my volume just in terms of height. So 1/3 pi, my radius is h divided by 2, and then I'm squaring that times h. So my volume is, well, I have h squared, squaring the h times that h. So that's going to give me an h cubed. Squaring the 2 in my denominator is 4 times this 3 from the 1/3. That's going to give me 12 in the denominator. And pi in here than the numerator. So my volume, simplifying that down, is equal to pi 12ths hr cubed. So let's take the derivative of both sides of the equation. We get dv dt. This is equal to, so bringing down my power, keeping pi 12ths out there, times that power 3 h squared. But height is changing with respect to time. Height is a function of time, so it's time dh dt. So let's simplify this. 3 goes into there 4 times. We know what the height is there. Height is 5. So we get that dv dt. And the rate of change hasn't changed. It's still changing at a rate of 10 inches. It's falling, so it's negative. Equals. So I have pi all over 4. H is 5. So 5 squared times dh dt. Let's multiply both sides by 4. We get negative 40 is equal to 25 pi all over 1. I don't need to put over 1 times dh dt. Trying to find the rate of change of the height. So let's divide both sides by 25 over pi. So we get dh dt is equal to negative 40 over 25 pi, which reduces as -8/5 pi. And this is changing with inches. The height is as inches per minute. So this would be our part B. So hopefully that was helpful.